Our last video introduced how to multiply a matrix times a vector. This video will generalize that and describe how to multiply two matrices together. So let me remind you of how to do a matrix times a vector. So if your matrix A has columns A1 up through AN, so has n columns, and your vector x has n components, then we define matrix multiplication A times x to be the column vector that you can create by multiplying the columns of A by the constants in x. So I'm going to do the constant x1 times the vector a1 and add that up until I get to xn times the column vector an. So I'm going to leverage that to define matrix multiplication. So I'm going to say, let A be a matrix with n columns, just like this situation, and let B, let's say B is another matrix. It doesn't have to have n columns. It could have m columns. So let's say B1 is the first column of the matrix B up to Bm. It could have any number of columns you'd like, but B must have n rows. So the number of columns in A has to be the same as the number of rows in B. Then what we define is A times B equals the new matrix that you get, and the new matrix has columns AB1 all the way up until I get to ABM. So the columns of the matrix are formed by doing this matrix times vector operation with the columns of B. So we have to see examples of this. What if I did the matrix, let's say 2, 1, 3, 0, 2, negative 1, times the matrix 2, 1, 1, 1, 0, 4. So this matrix has 3 columns, and this matrix has 3 rows. That means I'm able to do the matrix multiplication. If the number of columns here did not match the number of rows here, you can't even do the matrix multiplication operation. It's just nonsense. So what do? We form a matrix, and the first column of that matrix is the matrix A, this first matrix, 2, 1, 3, 0, 2, negative 1, times the column 2, 1, 0. That's the first column of the new matrix. And then the next column is 2, 1, 3, 0, 2, negative 1, times the column 1, 1, 4. Now we could do the calculation. When I do a matrix times a vector, I'm going to take the first entry of this vector, so 2, and multiply that by the first column of the matrix. Then I'm going to multiply 1 times this column, and then 0 times the last column. So I'm going to get 2 times the first column, so 4, 0, plus 1, 2. So I believe I get 5, 2 as the first column. Similarly, I'm going to do 1 times the first column, 1 times the second column, and 4 times the third column, and add everything up. I believe if you do that, you get 15, negative 2. So there's my matrix multiplication. Let's try to do this same two matrices multiplied, but in the opposite order. So what happens if I do 2, 1, 1, 1, 0, 4 times the vector, or the matrix 2, 1, 3, 0, 2, negative 1? This matrix multiplications can still be done because now I have 2 columns and I have 2 rows. So I can actually do this operation. This would be a new matrix, and that matrix would be the matrix 2, 1, 1, 1, 0, 4 times the column vector 2, 0. That'd be the first column of this new matrix. 2, 1, 1, 1, 0, 4 times the second column 1, 2. And then 2, 1, 1, 1, 0, 4 times the third column 3, negative 1. Hopefully by now you're catching on to how you do the matrix multiplication. So if I do a matrix times a vector, I'm going to do 2 times this first column plus 0 times the second column. That clearly just gives me 2 times the first column, so I get 4, 2, 0. You could do the other operations. I believe you get 4, 3, 8, and then 5, 2, negative 4. Now here's an observation. This matrix and this matrix are different. They're very different. Not only are all the entries different, but they're a different size. This is a 2 by 2 matrix, and this is a 3 by 3 matrix. So the moral of this story is that A times B is not equal to B times A. In fact, this is a very rare situation. If you give me 2 random matrices, it's almost never going to work, that A times B is equal to B times A. So you cannot reverse the order of matrix multiplication. In fact, sometimes you could do A times B, but you can't even do the matrix operation B times A. So for example, you can do the matrix 1, 2, 3, 4 times the column vector 5, 6. This makes sense. You could actually do the operation, but you cannot do the other order. So the column vector 5, 6 times the matrix 1, 2, 3, 4 doesn't. So not only is A times B not equal to B times A, as we've seen here, sometimes you could do one and not the other. Let's finish this video with one more example of matrix multiplication. So how about I let A be the matrix 1, 3, 0, 1. Then A squared can be interpreted to be A times A. So if I have an exponent here, like A squared, that just means multiply the matrix with itself a couple times. Now, if you think about it for a second, the number of columns in A, so the number of columns in A, in this case 2, has to equal the number of rows in A, which also must equal 2. So in order to do a squaring operation, you must have a square matrix. Square matrix means that the number of rows and columns are equal. So let's do this calculation. So this is the new matrix, and the first column of that matrix is 1, 3, 0, 1 times the first column, 1, 0. And then similarly, I do 1, 3, 0, 1 times the second column. And then you can do the matrix operation, and I think you'll find 1, 6, 0, 1. Okay, well, there was a very brief introduction to matrix multiplication. Wonderful.